So this is the third video, so I'm gonna be going from, I believe, it's this point, not this. So anyway, we're just gonna get started. So we have to create the filter. Yeah, so it's the 60 dB. Yeah, from here. I recorded this before, but it didn't work. But anyway, so we have to reduce the high frequency noise with 60 dB and then a 3 dB ripple. And then this will equal 0.5 in MATLAB. So I'm just going to do that now. And so yeah, so we say n omega is equal to both ord. So that's the 0.5 that I was talking about. When you normalize, then we have to do 19257, which is our noise cutoff, and we have to do divided by fs over hold on, fs over 2, and then that's 3 dB ripple, and then the 6 dB attenuation. So that will give us the order. So it's a fifth order. So then we create our butter filter. So we say B and A is equal to butter, and then we just pass in the order and the frequency. Yeah, frequency. And then we say we're going to create, so that's the first filter, and then the second filter is the second order filter. That is the stop band filter, or pass band. No, sorry, stop band. So we say B1 and A1 because we're going to be using that B and A soon. Is equal to butter. We're just going to create a fourth order series, and then we're going to create a 100 hertz stop band around the tone, the frequency we created. So it will be 2413 minus 50, and then 2413 plus 50, and then we have to divide that by over 2, and then we say stop. And that's that created. We're just going to check the if it is stable, so if it's inside the unit circle, which it is here, and then we freaks B1 A1, and then we're just going to set that to 10,000 so it's nice and smooth. So we check, first of all we just have to check what actually the tone frequency is in frequency, in the actual frequency that this value is. So we just say 2413 divided by fs over 2, and sorry, we're converting from frequency to our normalized frequency. So we're looking for 1094, so it should be centered around there, which 1006 it starts and it ends, and we should be getting close if we keep scrolling out. Yeah, we're getting, it goes to 93 dB, it attenuates, so we're attenuating quite a lot at that point. So then we're gonna filter our original signal using the first filter, and then we will pass this into our next filter, next one, so it's B1, A1 and Y, and then we're going to create our frequency axis as equal to 0 to the length of our input minus 1, and Just making sure I'm doing everything. Yeah. -1, and then that's divided by the length of our signal, our input, times fs, and then we can now plot these the both of the filtered signals. So we're gonna create y, fax, ABS, the absolute value over ft of the original signal, and then we'll say, so that's our original signal, so you can see the high frequency noise here, and then the tone as well. And then we will hold on, and then we will plot our filtered signal on the same graph, ft of y1, and we'll be able to see that. So yeah, you can see that the tone is completely filtered. I should zoom in a bit quicker. So yeah, you can see that's the stop band there at work, and then the high frequency noise is also completely filtered. So yeah, you can see it's just flat line there, and that's the filter. So the orange is in filter, the filtered signal. Now we're just going to label the axes. Y label is our magnitude, and then X. Oh, it didn't go on because I got rid of the. If I do this, and then hold on. I think that should pull it back up. Yeah, I didn't. I pressed the wrong Y label. Magnitude. X label is frequency. Frequency in hertz. Oh, missing that. X label. So yeah, we can see our frequency and our magnitude on the label axes. So now so that's that part done. So we have them two done. And so we did the applied, and then now we're just gonna phase shift of at least so pi over 4. So we're just gonna do a 45-degree phase shift. And so to do this, we will just find the frequency that this is applied to. Like we're gonna find a 45-degree phase shift. Because in our normalized frequency, we'll have to get it in our new in actual hertz. So we'll just look for a 45. So that's pretty close there. And we will then so take that value, if I can find it again. 18557. It's the one before this. 18557. So we'll just say 0.188. 185. 0.185 times fs over 2 to convert it. So we get that number, and then we will just create a tone. That's our frequency in hertz at that the 45-degree phase shift. We'll see a 45-degree phase shift between the original signal and this frequency. So tone is equal to cos. Is equal to cos of 2 times pi times this tone. So that's in 4079.2 hertz times t, and that should be good. And then we're going to say y is equal to, we're going to filter this, and let's say B, then A, and our tone. And then we're going to plot the tone. We're gonna hold on, and then we're gonna plot y. So if we go in, and then we zoom in, I'm just gonna do a horizontal zoom. So it should be like an eighth of a. I zoomed in too much. An eighth of a cycle, pretty much. So between the start, let me try. So that's the first, and then so one signal will go up and down, and then the distance, it'll be the distance between the peak here and the peak here should be an eighth. So it's looking good though. So that's 45-degree phase shift between our tone, which is in blue, and the Y signal. So yeah.